Okay, so today's lecture will be about all the necessary basics to understand all these techniques. Okay, and this will be the molecular basis of how the instrument actually works. Okay, and this is pretty much all the principles that you need to understand how any instrument that is going to be taught in the rest of the course is going to happen. Okay, how it works. First, let's deal with light. A lot of techniques that we're going to use today are going to deal with, not today, the whole course. It's how light interacts with matter, molecules, bonds. Light is nothing but oscillating electric and magnetic field. And it's propagating in a direction, and the electric and magnetic fields are oscillating in the direction perpendicular to the direction of propagation. And for example, let's follow the electric field. Okay, when the electric field oscillates up and down, and here the electric field, let's give it a sign, okay, positive. As it moves to the next cycle, it's actually negative. So the electric field goes from positive, 0, and then negative. The same applies to magnetic field as well. And there are some parameters based on which we can characterize each light wave. One is wavelength, which is the distance between two crusts or two troughs. You can take any waves and it's the same. So it's the distance between the points which are in the same state of oscillation or vibration. Okay? And that's denoted as lambda. And it has wavelength, the unit meters. Most of the light that we come across in our life, they are very small. They are order of 10 to the minus 9. That's why we use the unit nanometers. The other is frequency. The number of oscillations. So these things are going up and down. Number of oscillations happening per second. That's called frequency. And the energy of a light wave is directly proportional to the frequency. The higher the frequency, the higher is the energy the light can deliver. Now, for example, I'll give some examples here. For example, the red light. Red light is usually above 700, 650 nanometers, and blue light is below 400, 450. If you see, the color changes, accordingly the value also changes. Now, here are some of the examples of all kinds of light waves we have in the entire universe. We start with radio waves that have, the unit is here meters, the wavelength is in meters. And so the wavelength is increasing in this direction. That means the frequency will increase in this direction. And the energy, the same. Okay, the energy of these rays will be very, very high, and these rays are very low. Actually, as we are talking now, you guys can use your cell phone. That's because of radio waves, because they don't do anything. If there was gamma rays or X-rays in this room, it will be lethal to us. Okay, so that's a simple way of defining how energetic these waves are and how low energy these waves are. Now let's go and define what matter consists of. Of course, we know it consists of nucleus and we have electrons around it. If you take molecules, molecules are a collection of atoms which are bonded together. For example, here I'm showing, I think it's sodium chloride, I might be wrong, or no, I forgot what this molecule is. In every slide you will find there is a section called notes. How many of you know this? In PowerPoint there is a section called notes. Okay, I'll show you. When you download the slide from the course, okay, you escape and then you can see below. Can you see this? Okay, those, I generally give some notes there. Okay, there will be some additional information and also some links. So you guys can also look into that part. I forgot what was the molecule. It's sodium chloride. Okay, I remember it right. Yeah. So you have a sodium chloride molecule there, and the idea here is a bond is formed by sharing of electrons in the valence shell. Okay, and the extent to which the electron density gets transferred between two atoms decides what is the dipole moment. for example, let's take these two molecules, okay, atoms. Now, if this atom receives a lot of the electron density from here, so this atom is losing the electron density. So this will gain a partial positive charge because it's losing electron, and this will gain a partial negative charge because it's gaining electron. So there is a redistribution of electron density, and that is positive and negative. As soon as there is a charge separation, then it's called a dipole. And now, depending on the difference in electronegativity between these two atoms, you have different extents to which the electrons are redistributed. Here, let's say you take a carbon-carbon bond. Okay, these both atoms are exactly same, so they will have redistribution of electron density 0. So there won't be any impartial redistribution of electron density. On the other hand, if it is carbon and nitrogen, okay, nitrogen is a bit electronegative, more electronegative than carbon, so it will withdraw the electrons of this bond towards itself a bit more. So it will, delta stands for partial. It's not a full negative charge, it's a partial negative charge. The same here, these are ionic bonds. For example, sodium chloride. This sodium actually takes one whole electron it loses one whole electron. So sodium gets a complete positive charge. Here, what I'm trying to show is, depending on the electronegativity different, you have different dipole moments. Okay. So now, one additional thing about molecules is they're not static, they're not frozen. They all are vibrating because of thermal energy available in the universe. Okay, so there are different types of vibrations. Here I give just a few examples. And now, if you see here, I'm showing an example. It's water. Okay, a type of molecule that has a shape like water. It can undergo scissoring, stretching, symmetric stretching, asymmetric stretching, and here there are some more modes of vibration. Now, if you consider the situation that I was showing you the last slide, so there can be a dipole moment. A charge always emits electric field. Okay, that's the fundamental principle that we need to keep in the back of our mind. So if there is a partial negative charge, it will have its electric field. So does the partial positive charge. So when the molecule is, let's say this bond is stretching, and if it has dipole moment, it will create an electric field that is also fluctuating. And because of oscillation, you have molecules that create oscillating electric fields if it has a magnetic, if it has a dipole moment. If it doesn't generate any electric field. Now, let's go to the case where a molecule has dipole moment and it's vibrating. So it is creating a fluctuating electric field. Now, if you send a light wave, light is also electric field that is fluctuating. So now the electric field of light can interact with electric field of the molecule. And when the frequency of vibration matches, you have transfer of energy. Okay, this is the most important principle, which is called resonance, where one molecule can receive or lose energy from some other entity when they are in phase. The vibration is in phase. Okay. So now, for example, if you take a source of light and it has a fluctuating electric field, and if you take a molecule that has a bond that has non-zero dipole moment, a mode of vibration that has non-zero dipole moment, and if the frequency happens to match, then it absorbs radiation. So the initial intensity is I, and the transmitted intensity is I naught. Sorry, the initial intensity is I naught, the transmitted intensity is I. The difference between this is I naught minus I, and that is absorption. And this whole thing is the basis of infrared spectroscopy. Infrared spectroscopy, what we are actually measuring is how much molecules with bonds that are vibrating, that have non-zero dipole moment, can absorb light. And the exact wavelength of light, what wavelength it absorbs, depends on the energy of vibration. Okay, and that gives us an idea of qualitative. So what bonds are present decides which wavelength gets absorbed. And at a given wavelength, how much of light is getting absorbed, that depends on the amount of molecules that are present, and that gives us quantitative information. And here is a typical spectrum that we get. Okay, the percentage transmission. A higher amount is, a lower amount is transmitted, which means more absorption. Okay, that's how you're supposed to read the spectrum. So if there was a sample and they give the spectrum, then I can tell you that around this value, let's say 1200 centimeter inverse, there was a bond with a non-zero dipole moment in this molecule that absorbs in this region. And the intensity of that tells me how much of those molecules were there in the sample. Okay. Now let's go to Raman spectroscopy. So the previous infrared spectroscopy technique that depended on absorption, and this depends on scattering. Okay, I will go a bit into what is scattering. Now you have a propagating light wave. Here I'm showing only the electric field. Okay, so now as I told you before, the electric field fluctuates between positive and negative. And if you take an atom, when the electric field passes through an atom, let's consider this scenario. Okay, now the electric field is here. Now, as I told you before, a charge produces electric field, and the opposite is also true. So if you place a charge in electric field, it will experience a force. So now electrons are there in the atom. So as the electric field passes through, the electrons get redistributed. Okay, so this part of the atom will get a bit of more negative charge, and this will gain a bit of positive charge. Okay, now as it goes to the other side, the opposite happens. The polarity flips. So this whole process is called polarization. Atoms, molecules with neutral electron density, they undergo redistribution of electron density, and that process is called polarization. Now it can be expressed in terms of an equation. The energy of a molecule in electric field, if E is the applied electric field, now the energy is given by the initial energy plus the dipole moment times the applied electric field plus alpha. Alpha is the polarizability. In the next slide, I'll show you what is polarizability. Okay. Now, let's take two situations. One, an atom, a molecule which has zero dipole moment, and a molecule that has non-zero dipole moment. Now, the energy in the electric field is given, as I mentioned in the previous slide, as follows, where the dipole moment times electric field. Alpha is the polarizability. Now, because this molecule has non-zero dipole moment, this term contributes a lot to the energy term. Okay. Now, on the other hand, if you take a molecule with zero dipole moment, now you have zero dipole moment, so this term becomes insignificant. Okay. Now, this is the major contributing term. Polarizability is the extent to which a molecule gets distorted. That's how I would define polarizability. So now, if there is already a dipole moment, then the polarizability generally is low. It's very tough to polarize an already polarized molecule. That's a very approximate way of understanding this concept. Okay. So now, high polarizability would mean that there will be a stronger coupling. So now if you send a light wave through, now if there is a molecule with non-zero dipole moment, it will just pass through. But if it has zero dipole moment, there is a much higher chance that it will interact with matter. Now, in this case, the molecule has low polarizability, weak coupling with the light that is coming in, except the situation where the fluctuating electric field matches the frequency of incoming light. That's the only exception where it doesn't matter what the polarizability is, the light will interact. If you're talking in general about any wavelength of light interacting with matter, then the parameter that is most important is the polarizability. Okay. Now let's take the situation where you have a molecule with zero dipole moment, and there is an incoming light wave, and let's say we take a snapshot at this situation where the light wave's electric field is its highest. Let's say it's in this direction. So now because, as I told you before, electric field attracts electrons, right? Now, the electron, here it was neutral, the entire molecule was neutral, because in this direction, the electric field is pointed in this direction, the electron density will rearrange in such a way that the electrons will move closer to the end of this. Okay, so there's a partial negative charge here, there's a partial positive charge. Now let's take let's say a piece of matter, okay, which is made of these molecules. Now when you send a light through, most of it passes through, okay, but then once in a while something happens. Once in a while there is a light wave that gets coupled, like I told you here before, and that causes polarization difference. And once it gets coupled, it doesn't pass through. It has electromagnetically coupled with the matter, so it will be held by the matter for maybe a femtosecond or even a bit higher time scales, and then it's re-emitted. And the re-emission can happen in any direction. It doesn't have to have a relation with the path that is coming in. So the coupled light is randomly emitted, and this is the fundamental basis for scattering. This is what is scattering all about. Okay. So now we have learned scattering. It's about the electric field of incoming light wave coupling with the polarizability ability of a molecule. Okay. So now let's talk a bit more about what kinds of scattering can happen. Let's say this is the ground state of a molecule. Okay. Now when it absorbs the electric field of the light, okay, now it is excited to a higher energy state. What this actually means is, for example, if you have a molecule that is vibrating, when it absorbs a photon, it can go to a higher extension level. That's what I mean by the ground state is when the molecule is in its lowest energy form, and the EJ, that's when it's extended. Okay, that's what I mean by excitation. Now you have the ground state and you have molecule getting excited. Now the incoming light, let's say it has a frequency, which is the excitation frequency. Now when it's getting excited and it is losing the light again to come back to ground state, sometimes it need not come to the actual ground state where it started. It can come back to a virtual state which is somewhere in between the excited state and the ground state. In that case, the emitted photon has energy lower than the excitation photon. Okay, so in this process, the excitation photon has lost some energy and then scattering out. Okay, in that case, the loss of energy, those lines are called anti-Stokes lines. Okay, and the opposite can happen. Sometimes the molecule, as I told you here, the molecule got to this state, right? So now, if molecules get excited from this virtual state instead of the ground state, then it gets excited and it loses energy to come to the previous actual ground state. Okay, then the final energy is a bit higher than the initial excitation energy. Okay, so when you take a scattering spectrum, you will find three kinds of photons. One, there is the most intense photon population, which is the usual expected one, where the ground state and the excited state molecules come back to the ground state without losing or gaining energy. This is the most common process. But then you also find photons that have lost energy. You also have photons that have gained energy. Okay, these are called Stokes and anti-Stokes lines. Now, this is the basic setup for Raman spectroscopy. You have a source of light, and you have molecules that are Raman active. Okay. One thing, now I use the word Raman active. Okay. So now by this time I clearly made a distinction between molecules that have dipole moment and molecules that don't have dipole moment. And as you guys would have observed, for infrared spectroscopy, I mentioned they need dipole moment change. And for Raman, I started by telling we need high polarizability, right? So molecules, by looking at them, you can tell whether they will be Raman active or infrared active. Most of the molecules, if there is a bonding mode, there is a vibration mode, if it is Raman active, mostly it will be Raman inactive, but there are bonds that have both. Okay, but it's kind of a general observation that they are complementary. Raman and infrared are complementary. Okay, so now I'll go back to the setup for Raman spectroscopy. So you have a sample chamber, and then you send excitation light inside, and you measure the scattered light. In infrared spectroscopy, you measure the absorption light. And this is a typical spectrum. Here is Raman spectroscopy. Here is the wavelength. It's the frequency. Now here, the presence of this peak means there is a bond in this molecule that absorbs at that frequency, and the intensity of this peak tells you how much of this molecule is present in the sample. So now that's exactly what I've written there. You have qualitative, which is presence of a specific bond. You have quantitative, which is the intensity of a peak at a given wavelength. Now there is we are shifting. So now till now we have talked about vibrational spectroscopy. Okay, now we will deal with a technique that depends on a property of the nucleus. Okay, now we have dealt with a bit of electrons. We are going a bit deeper into the atom. Nuclear magnetic resonance. This is also known as MRI, magnetic resonance imaging in hospitals. The reason why they had to change the name was people, when they heard the word nuclear, they thought there is something nuclear. They're going to be injected or something. Patients were getting scared, and that's why they changed the name to MRI. Okay, so now everybody knows that you take any atom, it consists of a nucleus, and inside the nucleus you have nucleons, protons, and neutrons. Now, one of the intrinsic properties of every nucleon is that they have a spin. Okay, and generally pairs of nucleons, they have opposite spin. For example, two protons, they have opposite spin and they cancel each other. The same applies to neutrons. Now, if a nucleus has even number of protons, okay, so there won't be any net spin for the nucleus. The same applies to neutrons. If it has the total number of neutrons to be an even number, then it won't have any net spin. But then if you take nuclei with non-zero spin, so it might have an odd number of protons, it might have odd number of neutrons, or it can have both. Then these nuclei, they have a net spin, okay? And a spinning charged nucleus, it produces a magnetic moment. Some of the most useful nuclei are H1, which is a proton, and C13. If I'm right, in your NMR, you're going to have 3 extensive lectures on NMR, and I think they will deal extensively with proton and probably also C13. Okay, now if you take a population of, let's say, protons in a sample, they're generally the overall spin, the direction of spin is randomly oriented. Now, when you apply an external magnetic field, as I told in the previous slide, each of these atoms with a nuclei has a spin, and that spin, because of the spin, it has a magnetic moment. When you apply a magnetic field, which is, let's say, in this direction, the magnetic moment forces the atom with the nucleus to align itself with the magnetic field so that it doesn't experience repulsion. Now, this orientation or mode is called the parallel orientation, where in the presence of magnetic field, all the nuclei are pointing in the same direction. The spin of the nuclei are pointing in the same direction. But what you can do is, if you supply energy to this, the right photon energy, they will flip to oppose the field. Okay? And now, this is specific to a nuclei. Okay? Now, let's say you take a proton bonded to a carbon. It will have the energy required to flip it from being aligned to a magnetic field to opposing. That energy is different from a proton that is bound to, let's say, a nitrogen. Okay, so now different nuclei have different energy requirements to make this flip happen. Now, the energy, the broad range of energy, it happens to fall in the radio frequency. Okay, it's around 200 megahertz, and it's based on this flip, we can actually estimate the kind of nuclei present, the amount of these nuclei present. Okay, now the typical setup for a magnetic magnetic resonance instrument will be as follows. You have a radio frequency wave generator, then you have a sample, and then you have a detector. And you have an external magnetic field generator. So now you have sample where the spins of the nuclei are not aligned, and you apply a magnetic field, they get aligned, and then you excite the sample with radio frequency waves so that the spin becomes opposite to the magnetic field, and you detect the amount of absorption, how much of radio frequency has been absorbed in exciting the nuclei. And the chemical information is the exact amount of energy, what is the frequency of radio frequency wave that is being absorbed, that tells you which nuclei is present. Okay, now we'll go one step back. Okay, now I have given you 3 examples where you have the working principles of infrared spectroscopy, Raman, and nuclear magnetic resonance. As you see, the overall picture of this instrumental parts involved in all these methods is as follows. You have a source of light, you have a wavelength selector. I will tell you in a while why we need a wavelength selector. We have a sample holder, and then we have again a wavelength selector in case we need it, and then we have a sensor that detects the wavelength, intensity, etc. Now we will go one part at a time. What are each of these doing in the entire process? Now the source of light, the function of this is to produce a highly reproducible source of a specific wavelength. Okay. Now you have all kinds of sources which can be classified as follows. One is a continuous, which is it produces a wide range of wavelengths. Now, for example, some of our spectroscopic methods, they need UV light. Okay, we get UV light from a deuterium lamp, which produces from 190 to 370 nanometer. And then if you need visible light, then you need a tungsten lamp. I don't know how many of you have used UV vis spectrophotometer. Can you raise your hand if you have used? Okay. When you do a range from, let's say, 1000 or 800 till, let's say, 200 nanometer, you will most usually observe that at around 350 the instrument stops, and then it makes some sound, and then again starts working. The reason why that happens is, in the visible region, you use a different lamp, and then once you need to go to the UV region, the instrument has to switch the lamp. That's why if you do the measurement with UV vis spectrophotometer, you will see that at 300, 350, usually the instrument takes a break of maybe 5-6 seconds. Okay, and then you have sources that produce a line, which produces very specific wavelength, usually lasers. And each of these have advantages. For example, the continuous wave, they are generally very cheap, and they can produce a broad range of wavelengths. So if you can analyze a broad range of molecular vibrations. On the other hand, line spectrum, it produces one specific wavelength. Usually it's very high intensity and they have narrow bandwidth. Most common source is a laser. The advantage of this is the light produced, every photon produced is in phase. So they all are in phase with each other. So in some specialized spectroscopies where you use what is known as polarizability of light, it's the plane in which they are vibrating. If you use that property, which gives a lot more information, then this source of light might be useful. And nowadays, actually, we have lasers that are dye and also LED powered, and this has made use of lasers very common. In the beginning, I think 30 years ago, you could have lasers that could produce only maybe blue light, green light, only 3-4 wavelengths. But then now, because of dye and LEDs, you have the range of lasers available. The wavelengths that you can choose is much broader now. Okay, now we'll talk about wavelength selector. Now, as I spoke in the previous slide, you have a line emitter, in which case you don't need a wavelength selector. Okay? But if you are using a continuous wave source, okay, then you have to let through the sample only one wavelength at a time. So that it's like this, the way usually you do, let's say you are measuring the absorption from, let's say, 1000 nanometer to 200 nanometer. The way it's done is, you send one wavelength at a time, and then you measure the absorption, okay? And so the wavelength selector's role is to filter out everything that is not required and send through to the sample exactly that wavelength that is needed. And the same thing applies to the wavelength selector that is after the sample. Now, let's say the sample is emitting a signal, and you also have the light that is coming from the excitation source. Okay, so you want to filter out all the wavelengths, waves that you don't need, and only the useful information you want to send it to the detector. So wavelength selector actually plays the role of narrowing down the width of radiation that is either being exposed to the sample or which is transmitted by the sample, or also emitted by the sample. So now one very simple example for a wavelength selector is a prism. For example, if you have a white light passing through a prism, we all know that it splits up into the constituents of a rainbow. Now, if you want only yellow light to be your sample, your sample to be exposed to yellow light, what you can do is you can put a barrier here with a hole only at the region where yellow light is. So this is a very, very crude way of explaining what a wavelength selector does. Okay. Now, there are different ways in which you can achieve wavelength selection. One is using refraction, which is the principle that is used in a prism, and there is also dispersion. Okay. I will go into a bit more details how this works. Okay. Now, apart from prism, you can also use interference. Did I explain interference in any of those previous slides? No, right? No. Okay, so this is in one slide what is interference. You have a light wave propagating. Now, if you take two waves that are out of phase, okay, now if you see where there is a crust here, there's a trough here, okay, now they can add up to become zero. That's what is happening here. When you add one light wave to the other, it's basic addition. Okay, now positive becomes even more positive, negative becomes cancel each other. Okay, that's what is happening here. If they cancel each other, it's destructive interference. If they add upon each other, it's called constructive interference. And one of the most common ways to build a wavelength selector is by destructive interference of light. Here is the basis of how this is done. You have a surface of glass sandwiched between a thin metal film and dielectric material. Okay, now just follow as I explain what happens when light falls through. Now let's say a light ray passes through the metal film. Okay, now a part of metal film reflects part of the light and the remaining goes through. Okay, now as the light that passes through, it reaches the second metal film, it undergoes the same process, a partial reflection and transmission. Now the partially reflected light, it has traveled a distance. Now if you see, this is as it travels a distance, it also undergoes change in the phase. Okay, that's called path length. When it travels forward, the state of vibration changes. Now when this partially reflected light wave reaches this point, okay, now there is incoming light. Now the incoming light again is partially reflected and partially transmitted. The partially transmitted light, it interferes with this light wave. And now whether the light wave undergoes destructive or constructive interference depends on the actual wavelength that is coming in. And also the path length, how much distance it is traveling between this. Okay. So now, depending on the thickness of the dielectric we have, we can change the wavelength that undergoes destructive or constructive interference. Okay, so this is a way of selecting the wavelength that we need. In effect, after reflection, what happens is all the wavelengths that are not required, they undergo destructive interference, and only the light that comes out will be the light that undergoes constructive interference. Okay, so now we'll talk about another type of, it's the next type of wavelength selector that I'm going to use, talk about is very simple to understand, so that's why I'm not drawing any diagrams. For example, if you want to get rid, I'm very sure you all have sunglasses that are UV protective, right? The simple basis of that is you have molecules in the glass that absorb UV light. So when you send UV light, the molecules absorb the light that is not needed, and you're able to see properly because the visible light goes through. And that's the simple working principle behind absorption filter. So now absorption filter, you have absorption of range of undesired wavelengths and transmission of the desired wavelength. Now the question comes, what if we want to expose the sample as a sequence of wavelengths, one after the other? How do we achieve that? And that's when we come up with a wavelength selector that is capable of producing a range of, where it's not just one wavelength, it can produce a range of wavelengths depending on what we need. Okay? And these collectively they are known as monochromators, and mono means one, chrome is the word for color in Greek. And here is an example, very simple example of a monochromator which is based on prism. So now you have white light coming through, and as I told you before, it disperses into various colors. Now there's a slit here and your sample is here. Let's say if you want, now there is green light passing through the sample. Let's say you want to send red light. What you do is you turn the prism by a certain angle where this now goes through the slit. Okay, so this is a wavelength selector where it's monochromatic because it splits up into various colors, and it's also a variable monochromator, okay, where you can choose what wavelength you want. Now this is a classic example. I will give you a bit more technical example, okay, and that is based on diffraction. Now you have a reflector that is made of a grating element which has a lot of small stripes, and the distance between the stripes decides what the angle of dispersion. Okay, now you can choose. If you see the way the light gets dispersed due to diffraction, and then it is reflected by this focusing mirror, and now the different wavelengths are incident at different regions, and here you can put your sample here, you can put your detector here depending on what you need. And this is the principle behind diffraction. We don't have to go too much in detail into this, but these are two common ways of achieving light dispersion based monochromatization of light. Okay, now I want you all to discuss something. Okay, now if you have a sample holder, okay, now we talked about light source, okay, wavelength selector, and also wavelength selector after sample. Let's discuss what do you think should be the properties of a sample holder, the container that keeps the sample. What do you think should be the property? Can you use wood? Can you? No, because it doesn't let light through, right? So one basic requirement is it should let the light through, right? So it should be transparent, but it should not be just transparent to any light. It should be transparent to a specific light that we want to pass through the sample. Okay. Okay, I'll give some more clues. Okay, you guys are not opening up much. Okay, it should not interfere with the measurement. What does that mean? It means that it should not block the incoming light that has to interact with the sample. Okay, and this after the sample has interacted with the incoming light, either the light is scattered or the absorbed light is emitted again. Okay, so it should not, the sample holder should not interact with the emitted light. Okay, so in effect, what I'm trying to say is a sample holder should be transparent to the radiation of the region that we are interested in. Okay, now here are some examples. Now, for example, one of the most common sample holders that you'll come across is glass or plastic. Now, if you see for wavelengths below 350 nanometer, if your sample, if you're dealing with samples that absorb, or if you're trying to analyze something below 350 nanometers, then plastic is not suitable, and also glass is not suitable because they absorb in this region. For example, fused silica is good, quartz is good. Okay. The glass that you commonly use, it generally has not just silica. There are some things added. Generally, sodium chloride or some salt is sodium carbonate. Sodium carbonate is added to lower the melting point. And if it is above 350 to 2000 nanometer, then you can use glass silicate. Fused silica is actually 100% pure silica. And as I mentioned, glass or silicate that we commonly use in the kitchen, it's silica plus some salts. Okay, now the other part of this setup is the light detector. Okay, how do we detect light? We need to detect two things. One is intensity and the specific wavelength. The specific wavelength part, this takes care. Okay, the wavelength selector sends only specific wavelengths to the light detector. Now, the ideal characteristics of a radiation transducer or a detector is it should have very high sensitivity and it should have a very constant response over a wide range of wavelengths, and it should also have very fast response. Okay, here are some examples. Now, there are different types of transducers. One is photon, the other is thermal. Photon is where the light causes excitation of an electron. It knocks an electron out of the sample, or it knocks the electron out of the atom where it goes into the conduction band. The thermal transducer is where the photon gives rise to a rise in temperature. Okay. So now, among photon transducers, you have photoelectric. If you have a photon that is of very high energy, it can actually knock the electron out of the sample. Okay, then it can actually cause a current to flow, and generally the photocurrent transducers, they generally detect sample photons that are very high energy, for example UV or visible. On the other hand, if you take near infrared photons, they don't have that much energy to knock electrons out of the sample, but they do have enough energy to take the electron from the valence band to the conduction band. So the conductivity of the sample changes, and that's the basis of photoconductivity transducers. And you have infrared photons that are very low energy, but then we all know that infrared photons are capable of heating up samples. So now, for detecting infrared photons, we use what are known as thermal transducers, where the photon energy is converted into a rise in temperature. And the rise in temperature quantitatively tells you how much photons were incident. In each of this, for example, in the case of photocurrent, the current flow, the higher the photon, the more will be the current flow. And in the case of the photoconductivity transducer, it's the same. The higher the photon incident on the detector, the more will be the conductivity. Now, I'll summarize the first part of this lecture. That is, we started off with properties of light, the electromagnetic nature of light, and then we saw how light interacts with matter. We saw basis of absorption. We saw absorption. Apart from that, we also dealt with scattering, and then the overall principle behind vibrational spectroscopy, two types of vibrational spectroscopy, infrared and Raman. Then we also saw radio frequency absorption, which forms the basis of nuclear magnetic resonance, and then we moved on to general setup for optical spectroscopy, where we had the source, we have wavelength selector, we have the sample container, and then we have the signal transducer. And after a break, we will deal with X-rays and electron spectroscopy. Okay, we can have a 5 minutes break now.